So in this video we want to look at finding the angle formed by two planes. So if we have two planes, they're going to have formulas. Let's say if we have plane number one, it's going to be a sub 1 x plus b sub 1 y plus c sub 1 z plus d sub 1 equals 0. This is the general equation of a plane. And what we want to remember is that we have established that the coefficients on the x, y, and z term are perpendicular to the plane when we use them to construct a vector. So if this is plane 1, it's going to have a normal vector or perpendicular vector, a vector perpendicular to the plane. That's just given by the coefficients of the x and the y and the z terms. And if we have a second plane, a sub 2, let's give it coefficients a sub 2x plus b sub 2y plus c sub 2z plus d sub 2 equals 0. There's going to be a vector perpendicular to this plane given by its coefficients for the x, y, z terms. So there's going to be a normal vector, call it n sub 2, given by a sub 2, b sub 2, and c sub 2. So the first thing is we want to think about what happens if two planes are parallel. Well, if this plane is parallel to this plane, so let me draw a picture, a one-dimensional representation of this plane. We know that the vector of coefficients n sub 1 is perpendicular to that plane. So here's my vector n sub 1, and it is, by construction, we showed this in a previous video, it's perpendicular to the plane. So if I have a second plane, p sub 2 call it, and it happens to be parallel to the first plane, its normal vector will probably be a different size from the normal vector used for this plane, but the normal vector n sub 2, if the two planes are parallel, the normal vectors are also going to be parallel. And if they're parallel, that just means that the one vector is a scalar multiple of the other vector for some real number scalar other than 0. K can't be equal to 0 in this case. So they'll be equal to each other for some non-zero scalar k. If, however, the two planes are perpendicular, so here's my plane number 1 coming from this equation with its normal vector. If a second plane, p sub 2, happens to be perpendicular to it, then what we want to recognize is that the normal vectors, so this is the vector n sub 2, that's perpendicular to plane p sub 2, well, if the two planes are perpendicular, then the normal vectors must also be perpendicular. And what we learned from a previous result is if they are perpendicular, if n sub 1 is perpendicular to n sub 2, or orthogonal to n sub 2, then the dot product of orthogonal or perpendicular vectors is 0. So we can check to see whether two planes are perpendicular just by checking to see whether the dot products of the normal vectors are 0 or not. If the dot product is 0, we know we have perpendicular planes. If we have two planes, and the planes are not parallel and they are not perpendicular, then the two planes are going to meet at an angle. They would intersect at an angle, and we would get one angle of intersection would be acute and one angle of intersection would be obtuse. So if I have plane sub 1 sitting here, it's going to have normal vector n sub 1. It's going to have that vector of coefficients that's perpendicular to the plane. And so we have another plane that's neither perpendicular nor parallel to plane 1, called this plane sub 2. It's also going to have its normal vector n sub 2. And what we want to recognize is that if we put those two normal vectors toe to toe, whatever angle of intersection, the acute and the obtuse angle of intersection is for the two planes, the two normal vectors will have the same angles of intersection. So if we want to know the angle at which two planes intersect, we simply need to identify the angle at which the two normal vectors intersect, and we already know how to do that. We've already determined that if we have two vectors, we can establish the cosine of the angle between the two vectors, and that's going to be equal to the dot product of the two vectors divided by the product of the sizes or magnitudes of the two vectors. And then if we need to figure out theta, we just take the arc cosine of both sides and we can approximate that if we need to. So practically speaking, what that means is if I have two planes, say this is plane 1 and this is plane 2, this plane here is going to have a normal vector associated with it. So normal vector 1 that goes with plane 1 is just going to be from, we're going to extract it from the coefficients on the x, y, z terms. So we'll get normal vector with components -4, -6, and +4. And for plane number 2, it's going to have a vector that's perpendicular to the plane that we can also extract directly from the coefficients on the x, y, and z terms. So we get vector 2, 3, -2. And in this case, it looks like the vector -4, -6, 4 is just equal to 2 times the vector 2, 3, and -2. Let's see, this is going to be -2 times the vector 2, 3, and -2. -2 times 2 is -4, -2 times 3 is -6, and -2 times -2 is 4. So if n1, if the normal vector n1 is equal to -2 times the normal vector n sub 2, that tells us then that the two planes are parallel to each other because their normal vectors are parallel to each other. If we look at the second example, I have a plane here, plane sub 1, and a plane, plane sub 2. And plane sub 1 has normal vector given by -2, alligator bracket, 4, and 2. And the second plane, n sub 2, has a normal vector or perpendicular vector given by 1, 1, and -1. And if we look at taking the dot product of n sub 1 with n sub 2, we're going to get -2, 4, 2, dotted with 1, 1, -1. And that dot product is going to equal -2 times 1 is -2, plus 4 times 1 is 4, plus 2 times -2 is -2. And when we add this up, we get 0. And this tells us that these two planes are perpendicular to each other because they have normal vectors that are perpendicular. And we know the normal vectors are perpendicular because their dot product is equal to 0. So this last example, we have plane 1 and plane 2. And plane 1 is going to have normal vector n sub 1, which is equal to 1, -2, 1. And plane sub 2 has normal vector n sub 2, which is equal to 2, 3, and -2. And it would be easy to verify that they are not parallel, and their dot product, that this one is not a scalar multiple of this one, and that the dot products are not 0. So these two planes are going to meet at an angle that isn't going to be 0 degrees or 90 degrees. And what we can do then is, if we want to find that angle, we recognize that the cosine of theta is going to equal the dot product of n1 and n2 divided by the size of n1 times the size of n sub 2, which is going to equal. And then we could go ahead and work out the pieces here. The dot product is going to be the dot product of the two vectors, so 1, -2, 1, dotted with the other vector 2, 3, -2. And then the size of n sub 1 is just going to be the sum of the squares of the vector components, which is going to equal 1 plus 4 plus 1 is the square root of 6. And for this guy, the size is going to be the sum of the squares of the vector components, which is going to be the square root of, this is going to be 4 and 9, and 4 is going to be 8, and 9 is going to be the square root of 17. So we would pop that in here. We'd say, hey, look, I've got the square root of 6 times the square root of 17. And then we would need to calculate the dot product up here, which is going to be 1 plus -6 plus 1 times negative 2 is negative 2 over the square root. These could be brought together if we wanted to, so we could go, this is going to be 6 times 17 would be 60 plus 42 would be the square root of 102. And then simplifying, we get cosine of theta equal to, we get 1 plus negative 5 plus negative 2 is going to be a negative 7 over the square root of 102. And if we needed to find the angle, then we would just take the inverse cosine or arc cosine of both sides to get the angle we need. And this, of course, could be approximated using either your graphing calculator or GeoGebra. And then you would just need to make sure you were in the correct mode, radian versus degrees, depending on how you needed the angle.